talk about something that was one of the original motivations behind array programming, which is doing proofs on them, in this case mechanical proofs.
Yes, hello. My name is Nikolaj, and today I'd like to talk about a very much work in progress on doing mechanical proofs in an Array-Combinator language. And as you might have guessed, that language is going to be Futhark. It's work that I'm doing with Robert and Cosmin here. Okay, so first of all, what do I mean by mechanical proofs? I mean that specifically we want to be able to prove properties on arrays. And examples are written here, such as that an array is a permutation of another array, that it doesn't have any duplicates, or for example, that it's sorted. So we want to do this in Futhark, and Futhark is a purely functional data parallel language. And with me today, I bring sort of a running example called partition indices. And what this function does, this is sort of the Futhark signature for it. So it takes an array C's that are booleans of, we call them conditions, of size n, and then it produces an integer array also of size n. What this function does is it will partition the indices 0 through n minus 1 according to these conditions. So if I give it true, false, I get 0, 2, 1, and 3. So I'm able to use these indices later to permute an array according to the conditions. Okay, so what we want to be able to do is put annotations on inputs and outputs in Futhark so that you might be able to prove, for example, that this is in fact a permutation of 0 through n minus 1. And why do we want to do that? Mainly we want to use it to optimize programs, but you can also use it, for example, to verify the safety of parallel writes right here, like scatters, or that you're actually indexing arrays within bounds. And to give a motivating example of this, this is a scatter in Futhark. It takes a destination array as the first argument, then it takes an array of indices, and then an array of values to write at those indices. So the destination here is a bunch of zeros. It's denoted down here, or shown down here, and then we have the indices and the values. And then what scatter does is it writes these values according to the indices. So this is the example from before with the conditions. It will permute 20 and 30 here. So what could we use the fact that we know that 0, 2, 1, and 3 is a permutation of 0, 1, 2, and 3, which is the size of the destination array. We could, for example, use it to know that we are overriding all of the values here. That doesn't need to be the case with scatter. And so we wouldn't need to actually initialize this array. We wouldn't need to write the zeros. So that's one optimization. Another thing is that we can immediately infer that also the output of this will be a permutation not of the indices, but of the array values that we're scattering. Okay, and then finally, sort of more on the safety side, scatter has this thing that if since it writes in parallel, if you give it duplicate indices that write distinct values, so here we're trying to write both 20 and 30 to index 1. It's not well specified what this does since it's run in parallel. So you might want to, for example, show that the indices don't have any duplicates. Okay, so how do we go about doing these proofs? This is sort of a very simplified graph. So we have a program, then we want to generate some kind of queries for proving these properties, and then we want to hand those to an algebraic solver. So before we get into generating queries, which is really what I want to talk to you about today, I have a bit of context on Futhark. You got some of it already, but the array or Futhark programs are essentially compositions of array combinators, and the two most important of which are map, which takes a function, an array, and then applies that function to every element in the array. So here I have map with times 2 on 1, 2, 3, and I get 2, 4, and 6. A bit more fancy, we have scan, which takes an associative binary operator and a neutral element. So here this would be plus and 0, for example. And then an array, and it computes a prefix sum of that. So that's the first element in the first element location of the output, and in the second location you get the first two elements combined, and so on. So here 6 is 1 plus 2 plus 3. Okay. But as I said, Futhark programs are really compositions of these array combinators. So for example, you can write a dot product. I do it in kind of a funny way here because I only show you map and scan. But you can also map binary functions. So in Futhark you would write map 2. And then we can do a scan over that and take the last element, and then we get the sum of that. Okay, so this is to sort of say that the partition indices example that I showed you at first is really just a composition of these maps and scans. So what the function does, or how you implement it, is to first compute all of the indices for which the conditions are true. And then you compute the indices for which they're false. And then you combine this in the last line according to the predicates. I don't show you the false indices here, but trust that they are actually also just maps and scans. What I want you to take away from this slide is that we do bulk array operations that produce integer arrays, and we do them in sort of compositions, and in the end we get often arrays that we will use for indexing, so in a scatter, for example. That this is like a common paradigm of how you write programs in Futhark. Okay, so then we can go a bit into how do we generate these queries. And the first step we do is to model the programs as functions from indices to values. So the simplest one that I can write, for example, is for just an array. Here we have an array x is 1, 2, 3. And then we can sort of say that the domain of this function are the indices, so 0, 1, and 2. And then we can write x's as a function of I. So here it's I plus 1. We can also do this for the multiplication example. So here we write it as its own function that takes an array x's of size n and then applies this map to it. So here we see that the domain is now 0 through n minus 1. And the definition of the index function itself references or indexes into x's. Okay, so we have a restriction here that's not entirely obvious. So we only want to model integer arrays with these index functions. And to do this, we find it so far sufficient to restrict the values to what we call sums of products, and here right of terms, where terms are integers, program variables, array indexing, or sums over array slices, so very limited form of sums. And we do this in order to be able to actually prove stuff on it later. Okay, so I want to show you how would we derive an index function for partition indices, for example. And I'm just gonna go line by line and show you. So the first statement is a map with an if statement. So how do we handle this? We put cases on our index function. So this is a piecewise defined function. And this essentially means that these predicates or guards, they must partition the domain, which is 0 through n minus 1 here. And also they must be mutually exclusive. But we get that very easily from an if statement, likely. Throughout constructing these index functions, we also do a lot of simplifications. So one simplification you can do here, sort of to notice that this function is equivalent to just casting the booleans to integers. And so we get rid of cases like this, which is generally a thing we would like to do. Okay, so then we come to a scan, which is a bit more involved. And the way that we represent scans in general is as recurrencies. So we have a base case for I equals 1. This is the first element of the array. And then we have a recurrent case for all the other indices. That is the current element in the array being operated on, and then combined with whatever is the previous value of this index function. Here you might notice that now we have a reference to an intermediate variable, t flags, and our goal is really to come up with an index function that is describing partition indices in terms of its input instead. So we want to eliminate this reference. And the way we do this is by substituting functions into index functions into other index functions. So here I want to substitute t_flags into t_ins. And to do this, we first check that the domains are compatible. Here they are exactly equal, so that's easy. And then we combine all of the cases. So if we have more cases on t_flags here, we would just have a combination of those here. And then we can insert the values like this. So we lose the reference to t_flags. But what now if we would like to substitute this index function into another? If you do that, then you will just have a reference to t_ins I-1 still. So one thing you can do is to rewrite this recurrence in terms of the index function that you're substituting into. But another thing you can do, especially when you have scans with plus, is just to do a sum. So that's another simplification that we do. So hopefully you're convinced here that if you put I equal to 0 in, you will get a sum of only one term, which is C sub 0, and so on. We can continue doing this for all of the program, for fins and for the final statement. And then what we get in the end is an index function that looks like this. And just to convince you that this, what this actually says, this is our true indices from before. And you can sort of convince yourself that if you put an I in here and the condition is true, then the index that you get out is the sum of all the true conditions minus 1 to get an index. And in the other case, if it's not true, you are sort of at position I in your array, but then you shift to the right by the number of conditions that are true that come after you. So this goes from I plus 1 to n minus 1. Okay, so now we also have this annotation that we want to prove a permutation of something. And from this, we can generate a query that says that these two branches are non-overlapping. So the indices that you get from the two branches are distinct. And moreover, there are no duplicates in the first branch, and there are no duplicates in the second branch, and also that they cover all of the domain. So we have, it has to be start at 0 and end at n minus 1. So hopefully that convinces you that we can generate queries for programs like these. What we then do is we hand it to an algebraic solver. And the way that our algebraic solver is kind of naive, it has, how it works is kind of naive. We have an environment of ranges on variables, and then we have expressions wherein we want to eliminate these variables. And I just want to show you that, of course, a program gives you ranges on variables, but these index functions also extend these ranges. So here, for example, you immediately have that I is bounded between 0 and n minus 1. But we also have that, of course, casting a condition to a Boolean to an int bounds its value between 0 and 1. Okay, so we had our query. How do we actually go about formulating something that can be proven here? Specifically to prove this no duplicates, we would like to show that if we have two indices, one being less than the other, then inserting this first index into our branch that we are currently in will lead to a value that's less than if we use the later index. And why do we want to show this? Well, if we can show that why is this sufficient? Oh yeah. So if the value at a later point is always greater than at an earlier point, of course you can't have any duplicates. The way that we encode these ranges for I1 and I2 is shown to the left. So you could say that I1 is less between 0 and n minus 1, and that I2 is between the maximum of 1 and I1 plus 1 and overrounded by n minus 1. And moreover, because we are interested only in this blue case, we also know that this predicate is true for I1 and it's true for I2, which means that this will be 1 for I1, like if you insert I1 in here. And we also put that in the range environment. And then we give this to what we call a Fourier-Motzkin elimination-like solver. What it will do is it will iteratively insert these ranges, try to eliminate the variables in that sense. And if you can keep doing this until you don't have any more variables, then you have something that's can be statically determined if it's true or, yeah, well, if it's true. And if you can't eliminate all of the variables, then the result is not that you cannot show this, but simply that we don't know, in a sense. Okay, so to give you a sense of why this is Fourier-Motzkin-like and not just Fourier-Motzkin, basically we have to extend such an algorithm with rewriting of sums, but also for using array properties that we might have already proven. So the first step you could do here is to subtract the left-hand side from the right-hand side, and then you get a sum from I plus 1 to I2. And then you can split a sum like this. So now we are just splitting out the term that's I2, and then you have a sum from I plus 1 to I2 minus 1. But we already knew that this, from the range environment, can be eliminated to 1, and then we have 0 less than 1 plus some sum. But we know that from the blue range environment that this is a positive, always positive term, which means there's monotonicity in this. So that's to give an idea of the kinds of things you have to handle in this solver in order to prove these properties. Okay, and then from here you can use array properties further on in the program to derive other index functions, and in the end you could also use it to verify, optimize the program, which is our goal. So that's mainly what I wanted to say. I think I have like 1 or 2 minutes more. So maybe I wanted to show you our prototype. So what I showed you today is sort of a very simple program. This one, in fact. So if you run our prototype in the compiler, oh, we don't get the end. There you go. Then you can sort of, this is in a different notation, but you can see the index function that we've derived in the slides. But you can also see all of the intermediate index functions. So as a user, you might want to see these index functions, and then you can see them for each statement in your program. So it's like there's a one-to-one mapping between the index number, or like the names here and the names in your program. So this is, of course, a simple example for partitioning indices, but let's say you have an irregular array that is flattened, and you want to partition segments of indices. Then it gets a bit more hairy, and this is just to show you that this does get less pretty, but it's sort of doable. So we get an index function with 4 cases in this case, and you could imagine the complexity gets greater or worse from here. But this is our prototype so far. That's all I wanted to say. Thank you for listening.
Questions?
You said you are motivated partly by being able to do better optimizations. I was curious, like, what is an optimization that is possible with these proofs?
So one of the examples I had was if you're scattering, sometimes you scatter into a destination that's much larger than the values that you're writing. Sometimes you're scattering into an array that's actually smaller than the values that you're writing. But if you know that you're overwriting all of the values in the destination, you could not initialize that destination, for example.
Thank you for the talk. I had a question about the choice of modeling those algebraic properties with sums of products and some other things thrown in, I suppose, as well. So is this choice, well, maybe I'm just ignorant of this, but is this choice motivated? Is this like a model that people have used before? Because it also, the way you describe it, did you roll your own solver, or is this like a solver that already exists?
So the solver is actually one that we're writing. Robert is writing it. But it's very naive in a sense. So we only have these ranges, and we need to do a lot of sort of partial evaluation in a sense. I don't know if that's the right word, but we need to simplify these statements a lot. And that's possible when you have such a restricted representation. It's much easier to normalize it when you are restricted to these sums of products. And I think that's a key thing that we are relying on in order to actually be able to prove anything in practice.
Okay, that makes sense. Thanks.
So for your example, you're trying to show that there are no duplicates. Would it make sense, instead of just saying giving the user the feedback, I don't know, then you can try to prove that there is a duplicate, and then you get particular evidence?
That's a good question. Yeah, because the way that we use the solver is that either we get a yes answer, this is true, or we get an I don't know answer. So definitely you could turn it around and then try the other direction as well. That's a good point. And actually, I also do this in simplifying some of these cases. So I will, for example, like I might not be able to prove that something is always true, but maybe sometimes I can prove that it's always false in a sense. So I try this in the simplification.
Can you go to the slide right before you generate the queries?
This one?
The one with a code.
This one?
Yes. So in the let t flags line, you're applying a function to this CS variable.
Yes.
Is it possible to just remove the CS variable and let the t flags be a function? Then that way the second line t in the indices would also be a function instead of a variable of an array. Then just delay all the function application until delay all the function on variables until the last line. So the rest of your program, so everything below it are just the functions instead of arrays. I'm
not entirely sure that I understand. In a sense, the C's is already an argument to this function.
But the C's is the CS is not a function, right? It's a Boolean.
It's a Boolean array.
What's on the right-hand side, that's the compiler representation, static representation for the arrays.
Right.
So it's not something that is
Right. So, but in terms of evaluation, right, you can just have everything be, just define a bunch of functions at the start, then compose them at the end when you apply it to your actual array.
Yeah.
So would that idea also work in this case if you structure your program like this?
So if I get what you're saying, it's sort of, so if you took all of these, I think it would be much the same actually, because here it doesn't have to be an array. It could be an expression, like you could write map. Maybe this is what you're asking. You could write map here, so you have an expression here. And the way that it's done then is that just you create the index function for this first, and then instead of having an intermediate variable for this in the environment, you just substitute it in here immediately.
Yes.
So yes, that works.
And can you write this whole let expression as a one-liner?
Is it one-liner? Yeah, sure you can.
Great.
I think so, at least.
Any more questions? Yeah, thank you for this talk. This kind of cuts close to somewhat some of the things I'm interested in, just on my side playing around with things. I'm curious if you can productively produce proofs. It seems like, so if I understand correctly, you would need to declare, with your current system, you have to declare what kind of constraints that you want, and then you prove whether it holds or not. Would you, is it on your radar at all to have sort of some kind of tactic system where you could have some properties produced and inferred from just previously designated properties on the system? So like you could say, you know,
So
without declaring that it's going to be a permutation, but you know some of the sub-expressions that you're using force it to be a permutation, you'd be able to just infer it directly. And then the programmer could see, oh, look, this is going to be a permutation or something, maybe use that information.
I mean, it's a possible route. I think we're too early to care about stuff like that at this point. But for example, one thing that we care deeply about is inferring these index functions. And the index functions have a lot of information, for example, such as that. So maybe it could be a thing.
Thank you very much.
Yeah.